So, dear pupils, we have made something, I would say, astonishing. Okay? We have defined surfaces, not as we usually think of surfaces as some thingy, okay? But we have given a very rigorous definition based on the idea of a surface being just a set of points in space where my movement is reduced or can be reduced to a movement in just two directions. That can be reduced locally to a movement in just two directions. Why do I say locally? Because if we think of generic surfaces and we think particularly of that of the cube, okay, the movement here in this face of the cube can be reduced to these two directions, but in this other face it's reduced to two directions, but different from the first mentioned, these other two, for instance, okay? So you see, I say locally because I mean just in the surroundings of some points, okay? This is just a nuisance I wanted to introduce. The general idea is that we have managed to define surfaces as a set of points where my movement can be reduced to a movement in two directions, something which is quite surprising as a definition, nothing to do with what would come first to mind, I think, when thinking of surfaces. And we have even given another one based on the concept of coordinates as a set of points where the coordinates of the points are linked in such a manner that knowing two coordinates, I can define the third. Surprising once again. I think we would never have thought of surfaces to be something like that, okay? Maybe the idea of us when moving on a surface, for instance, this of the orange, not being able to move in some directions because I can't move on any of these, okay, could give us some clue, okay? But once again, I insist on the artificial character of these definitions, nonetheless perfectly valid, of course. But this idea of not being able to move in some directions could point us to our final approach to a definition of, to a proper definition of surface, which is that particularly we can't move in this direction, okay? When we move on the spherical surface, for instance. We can move in a direction that we could call thickness, okay? And then we would be presenting or defining surfaces as shells, okay? As envelopments of volumes that have no volume themselves, okay? So this is what we are going to be speaking about thickness. And we need to know what thickness precisely is. We need to define thickness. Once again, emphasis on definitions. So we all intuitively know what a surface is. We all intuitively know what thickness is, okay? If we have this roll here, we all know that it's the thickness of this in this point is this one, okay? This one I am measuring with my two fingers. But in some occasions, in some situations, it's not so intuitive. First thing I want to highlight, thickness is not a property of volumes, and it isn't a property of surfaces. Thickness is a property of points in surfaces that are enclosing a volume, okay? That's the idea. Thickness is a property of points. And something that we intuitively know, I want to highlight, okay? The fact of thickness being measured somehow perpendicularly or towards the center in volumes, in surfaces enclosing volumes, okay? We'll intuitively know that this is the direction where thickness is to be measured. We don't measure it like this, or this point. We don't measure it like this. We don't measure it like that. We say, no, it should be like this, towards the center. Let's insist on this idea, perpendicularity and center direction as the direction where thickness is to be measured. And let's see it with some examples that are going to show you how this can be a little bit tricky. Let's try to find the thickness of different points in the surface enclosing the volume of this rectangular prism. Okay, this rectangular prism, this triangular prism. Okay, it is composed of two inclined planes. Okay, one rectangular base and two triangular walls. By the way, 5 faces. And how many vertices? 6 vertices equals 11, which will be equaling the number of edges plus 2. So the number of edges is 9. But getting back to our thing, let's find those thickness. Let's consider a point. Here you can count if you want the edges. Let's find the thickness at a point A, which is on the base, on the rectangle of the base. Okay, we will just draw a perpendicular up. Okay, till it intersects the inclined plane. So if the base is here, the point under consideration is, if the base is here and the point under consideration is this one, this distance would be the thickness, defined by the segment AB, being A the point under consideration, and B the intersection of the perpendicular to the base with the envelopment, with the inclined plane, the exiting point, let's say, of the line defining the thickness direction. Okay, AB would be the thickness at A. If you want to, you don't see what I mean, maybe in this picture you see it more clearly, in this drawing you see it more clearly, or even in this one, which is just a frontal view. Okay, a frontal view, or we are seeing it like this. Okay, so we are drawing our perpendicular, we are finding the exiting point, let's say, of the volume, and that's the thickness. But what's the thickness at B? The thickness at B would be defined by, generally speaking, by a perpendicular to the plane and finding its exiting point, finding the exiting point of the volume, finding where it intersects with the enclosing surface. Something like this. We will be getting to some point C here, and this distance BC would be the thickness at B. So the thickness at A is the distance defined by the segment AB, and the thickness at B has nothing to do with the segment AB. It's a new segment, BC. Okay, so all this to put an emphasis on the fact of thickness varying as we move in the surface enclosing the volume. Okay, the thickness is not a constant value as happens here. This is just a very particular case where the thickness is constant in all the points of the surface enclosing the volume of these two, defined by these two cylinders, let's say. Okay, but in general, thickness will be varying. It's a property of the points enclosing the surface, enclosing the volume. Okay, of the points of the surface enclosing the volume. Please try to remember it. So fantastic, but we have worked with planes where the idea of perpendicularity, it's intuitive, okay? We know that this line is perpendicular to this plane, and we know perfectly that this one isn't, and that this one isn't, and of course this one isn't at all, okay? But how can we define perpendicularity in any surface, in our loft wavy surface? How can we do that? Or in an orange, okay? How can we do that? Let's see it. So the answer is easily put, but not so easily explained. Not so easy to explain, okay? The answer is that the direction on which we measure thickness at a given point of a surface is that defined by the perpendicular to the tangent plane in that point to that surface. That's it. Not so easy. Or maybe yes. Maybe yes. What's a tangent plane? What's tangency? Okay, let's first try to work out what do we mean by tangency. Okay, first imagine the circle defined by this rule. Okay, just forget about the volume, the inside cylinder. Just consider the circle here. Okay, what's a tangent? What's a tangent to that circle, to that circumference, to be more precise, okay? Lines, in general, will be cutting the circle in 2 points, like here, okay? In 0 points, like here, or maybe in just 1 point. This is the tangent, a straight line cutting, or touching, if you prefer, the given line, the given curved line, in just 1 point. And that's the definition of tangent for curves in planes. What happens with surfaces? Something a little bit more complex. It's a little bit more complex because if instead of considering just the circle here, okay, just the circle here, we consider the whole surface, that in brown, we see that, yes, it is true that at this point, this line is tangent. But these all other lines I am describing right now with my ball pen, okay, are tangent as well, okay? They are tangent as well. They are touching just in 1 point the surface. It is true that this particular line is touching in an infinite number of points, okay? But just please forget about it. And if you don't want to forget about it, just think that it doesn't get inside the volume enclosed by the surface, okay? So, as you see, there are an infinite number of tangents to a point in a surface, okay? But luckily, all those lines are in the same plane. All those lines are defining a plane. So, in plane lines, in lines defined on a piece of paper, let's say, the tangent is a line. But on surfaces, more generically, in the 3D space, in fact, in lines in the 3D space, the same thing happens. The tangent is not a line, but it is a tangent plane, as you see here, okay? I think that here, with this pad and this orange, we are getting the idea of tangency, of tangent plane. Okay, let's see, maybe here you see it better. Okay, so there you have it. There you have it. And even if I put it perpendicularly to you, you will be seeing the concept of tangency of a circle, okay, the tangency of a circumference, okay, and now you will be seeing it as a matter of surfaces. So, in any case, tangent to shapes in general, a plane, okay? But how can we find that plane? Okay, we can work it out, as you see, with some thingies, but how do we do it mathematically? There are 2 ways. Maybe more, but I know 2 ways, okay? One of them is by the use of derivatives, okay? But it's something that I think that it's not for now, it's for later on. Okay, we were saying that we were with the Greeks, and I think we are getting too far away from the Greeks, okay? So let's keep the derivatives on one side for the moment. Let's do it as the Greeks did by means of approximations, but very particular approximations. Approximations that can get as good as I want. What do I mean by this? You have a line, draw a line in your imagination, make it something like this, okay? We can approximate it by means of straight lines, by means of segments. If we do it wisely, we will be defining some kind of path that will drive us to get as close as we want to the actual curved line by means of these small segments. Let's try to see it with an example. Let's bring back our black line, which we have already worked in some videos. Okay, I can approximate that black line by means of straight segments, just dividing into segments the line and drawing connecting lines, okay? You see it here. Is this a good approximation? I don't know, but it's an approximation. The line at least, it's something close. I mean, it's not making something like this. It's reasonably close, and we can improve, of course, this if we divide against the segments present in this drawing in 2 segments more, okay? We divide them again into segments. We do it like this, okay? And then we connect the points. And now we are getting, once again, closer to the final shape. And I could repeat this once again. Now I will be having something like 9 points, I think. And now I am quite closer. And of course, I think this is not bad considering that we just have made 3 iterations of our method, okay? If we make, I don't know, 30 iterations, just imagine how precise our blue line would be when compared to our black line. They will be very close as I want. If I want to make 40, if I need more closeness, let's say, I would make 40, 50, 100 iterations of this process, okay? And of course, there are a lot of different methods. This idea of dividing it on equal segments, it's just one idea that describes a path that I tell you it's going to take you to the line, okay? But we can use different methods. And one very interesting would be to include at some stage of this iteration process the maximums and minimums of the black line into the process of drawing our straight segments, okay? Those maximums and minimums, those peaks and valleys of the black curve are, if you pay attention to this and if you think about it, you will see that and wait a moment, let me rescue my pointer, that those points of maximum and minimums are points where the tangent, by the way, it's horizontal. The tangent at this point is a horizontal line. The tangent at this point is a horizontal line. At this one, the very same. This we will be seeing much later on, okay, when we enter into derivatives precisely. So if I add here, as you can see on your screens, if I add here the minimums and maximums, and then I draw my blue line, okay, and I have just added 4 more points, now we have something which is very, very close to the actual shape that we have been given, to the black line, okay? So this is the idea of approximating lines by straight segments, but of approximating them with a method that gets us as close as we need to the actual curve, okay? That's important. It's not just an approximation, it's a method of approximations that describes some kind of path directing us towards the actual curve we want to work with. And now we can get to the notion of tangent, okay? Think that in this process, a point P on our black line will be matched by a point P1 in the first iteration, by another point P2 in the second iteration, etc., etc. These points will be in different blue segments, okay? Let's call them SP1, SP2, SP3, if we are in the first iteration, second iteration, third iteration, etc. That will be, in general, getting smaller as we advance in our iteration process, in our approximative process, and will be tending to stabilize around a particular direction, okay? Around a particular line, let's say. If we see it on the screens, okay, you see what I mean by this would be the point in the first approximation, P1, P2, P3, P4, and these would be the segments SP1, sorry, I don't have my pointer, P1, P2, P3, P4, I said, and these would be the segments SP1, SP2, SP3, and SP4 that, as you see, are trying to stabilize somehow into a given line, into a given direction. With other points, it might be seen better. That direction is a tangent. That direction, those segments, those lines are tending to is the tangent. Nothing more and nothing less. Okay? Some occasions we will be able to calculate precisely to what are those lines tending, okay? In other occasions we won't be able. For instance, if we are given just some points of the line, pin, 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 we won't be able to say exactly what happens in terms of tangent in one point. But if we have a continuous line described by by an equation, as it happens in analytical geometry, and we are given the formula, let's say, by means of the derivative, we will be able to calculate the value of the direction of the tangent. Okay, so that's it. That's the tangent. Something as simple as that. And this idea of getting closer to a direction, getting closer to something, is the idea of limit. What happens when we have made an infinite number of iterations? When we have made an infinite number of iterations, we will be getting, as our segment, SP sub infinite, would be the tangent. Okay, that's the limit. What's the idea of limit? Examples of limits. If I tell you 1, 1.9, 1.99, 1.9999, 9999, etc., if I give you that succession of ordered numbers and I tell you what's the limit, you're going to tell me 2. It's going to be the number 2. Okay, so you have clear in your mind the idea of what a limit is. It's something that we are getting close to. Okay, another example of limit is in the 100 meters. Okay, in the Olympics or just in any 100 meters run, there is a world record. Okay, those world records are being reduced every 2, 3, 5, 10 years, but they are getting reduced. We don't know what the limit of that reduction is. We don't know if it's going to be 9.6, 9.5, 9.43, but we know that it exists. We don't even need to know what the actual value is to know that there is a limit, that every time we are going to be getting closer and closer and closer to a final figure which will be never beaten. Okay, that's the limit. Limits, pay attention, are not limited to limits of succession of numbers. As we just saw, we can be working with limits with lines that are stabilizing around some particular line, or planes, or different shapes. You may have seen these videos of the man as a result of the evolution of an amoeba after a dinosaur, later some kind of mammal, later blah blah blah, later an ape, and finally a man. That can give you an idea of a succession of shapes that can be pointing towards some direction, towards something. Okay, and of course we have this in your screens. Okay, this succession of regular polygons is clearly pointing towards something, towards a circumference, no doubt about it. It's not a matter of the figure number 100 being a circumference. It's not, but for us, seeing it in this context, we can see that it's a succession of polygons pointing towards a circumference. Okay? And all this was to see the idea that we can calculate tangents to curves, okay? But we said that our problem was a little bit more complex because our problem was to calculate tangents to surfaces. How can be that done with the help of this idea of approximations by means of simple things? Curved lines, we can approximate them by segments. How can we approximate to surfaces? Maybe by means of polyhedrons, of surfaces made out of flat surfaces themselves, okay? For instance, small triangles. I can make some kind of, I don't know, net in this orange, firstly of 10, then of 100, then of 1000 points. That could be, for instance, equidistant or something like that. And connect those points by means of lines forming triangles. Each time the triangle will be getting smaller and smaller and smaller. And as we had with as it happened with our line, though each point of the surface of the spherical of the orange will have a matching triangle, let's say, in each iteration. That triangle will be, as we said, getting smaller and smaller, and the triangle will be defining at each iteration a different plane, because 3 points define a plane. Okay, if you give me 1, 2, 3 points, there is always one and only one plane passing by those 3 points. So that plane, each triangle is defining as we change of iteration. will be stabilizing around some particular plane. That plane will be the tangent on the point at, or will be the tangent at the surface on the point under consideration. Okay, so this is the idea of tangency. And as we said, the direction on which we have to measure thickness at a point of a surface is that of the perpendicular to the plane tangent to that surface at that point. Okay, so something like this. We will be measuring its entering point, let's say. We will be finding its exiting point, and the segment connecting those 2 points is the thickness of the point under consideration. As simple as that. Now we are in a position to get 2 surfaces as the limit of a succession of volumes. How is that? Okay, we will get to the cylinder, represented by this brown surface here. We will get to the cylinder as the limit of a succession of, let's say, cylinders. Okay, we will be making this thickness here, we will be making it, we will start here and we will be making it smaller and smaller till we get to the limit, which would be our surface. And I have to think on how to put it mathematically or more rigorously, but the idea is that we will define surface as the limit of volumes. Volumes don't need that much of a definition, I think. I have to think about it as well. So, next video, or just let me some hours to think about that and we will go on.